And on to the second question. I deliberately chose this question because it is really the worst question on Unit 8 the IB has ever asked. Back when I was head of physics, I used to put this in every Year 13 mock, and it almost uniformly went really badly. In my opinion, parts A and B in particular are quite difficult to get your head around. I'll describe those. But you should all be able to answer parts C and D, and what I've found from a lot of students is that they try A, not know what's happening, look at B, panic, and then just move on to the next question. But you'll notice that both A and B tell you what the answer actually should be, and therefore you can answer C, and indeed D, which is a written answer question, without having even understood where A or B are coming from. And you'll also note that part C, although much easier, is worth the same number of marks as A or B. So it is well worth persisting throughout these exams. The Sun has a radius of 7 times 10 to the 8 metres and is a distance 1.5 times 10 to the 11 metres from Earth. The surface temperature of the Sun is 5,800 Kelvin. Show that the intensity of the solar radiation incident on the upper atmosphere of the Earth is approximately 1,400 watts per metre squared. So there's several things I need to do here. I need to work out the power that is output by the Sun, and then I need to work out how much of that power reaches the orbit of the Earth. So effectively, I'm working out the power output at the surface of my Sun, and then the attenuation of that by the time it reaches the Earth. So I'm going to first look at the power output by my Sun, which is given in my formula booklet. Your formula is E sigma A T to the 4. That's the emissivity. For this question, I'm going to model the emissivity of the Sun as just 1, and that is actually a reasonable approximation. Sigma is Boltzmann's constant. A would be the surface area of the Sun, and T to the 4 would be the temperature of the Sun to the 4th power. So in this case, I have emissivity of 1. Boltzmann's constant is 5.67 times 10 to the minus 8. Then your area of a sphere, it's in your formula book, is 4 pi r squared. So 4 pi times your radius, so that's 7 times 10 to the 8 all squared. And then your temperature is 5,800 to the power 4. And so there you have your power output by your Sun. But you want the solar radiation intensity, so power per unit area, incident on the upper atmosphere of the Earth. So your intensity is your power per unit area, but crucially it's at Earth's orbit. And so that is the power of our Sun, 5.67 times 10 to the minus 8, times 4 pi, times 7 times 10 to the 8 all squared, times 5,800 to the power of 4, but then the area here is not the surface area of the Sun. We've already worked out the power being sent out. It's the surface area of the sphere traced out by the Earth's orbit. So in other words, it's still 4 pi r squared, but now it's 4 pi times 1.5 times 10 to the 11 all squared. I can tidy this up a little by cancelling my 4 pi's. And so I have 5.67 times 10 to the minus 8 times 7 times 10 to the 8 all squared times 5,800 to the 4th power. And I'm dividing that by 1.5 times 10 to the 11 all squared to give me, thankfully, 1397 watts per metre squared, which is approximately 1400 watts per metre squared. Once again, I'm going to more SF, and in fact the mark scheme specifies it would have to be 4 SF if you wanted that mark here. But I'm going to more SF than the answer given, so that I show the examiner I really understand. There are 3 possible ways to get this mark. You can either get a mark by doing E sigma AT to the 4 divided by pi, or 4 pi, d squared. Or you can get it for subbing all your values incorrectly, or you can get it for 1397. So they did allow all of your working not to be perfectly coherent, but you did need to show very clearly that you weren't just guessing numbers to get to 1400. As with all show that questions, really. Part B, the albedo of the atmosphere is 0.3. That means 30% of all radiation is reflected from the atmosphere. To deduce that the average intensity over the entire surface of the Earth is 245 watts per metre squared. So if 30% of radiation is reflected from the atmosphere, then 70% gets through. So this is my transmitted intensity. So 0.7 times 1397. Notice I'm using my unrounded value, gives me 978 watts per metre squared is transmitted. if we think about the Earth as a sphere, so let's use this little ornament here. If we think about it as a sphere, then your solar radiation comes in and it hits just like a circular face of that sphere. Effectively, it hits the two-dimensional representation of your three-dimensional sphere. So imagine if I shined light onto this sphere, I just get a shadow of a circle. And it's the same thing here. Your light comes from the sun, it hits a circle of the Earth, pi r squared, where r is the radius of the Earth. However, you want to know the average intensity over the surface of the Earth. So the area that's hit by the sun is pi r squared, where r is the radius of the Earth. You don't know that, in fact. But the surface area of the Earth is 4 pi r squared, where r is the radius of the Earth. So our r squareds cancel, our pi's cancel, and effectively just the ratio of the surface of the Earth that is hit by the sun compared to the total surface area of the Earth is 1/4. So I know my average will be 1/4 of 978, which is 244.5 watts per metre squared, which is approximately 245 watts per metre squared. Once again, going to more SF to show I understand. And they're the hard bits of your questions over. So it's recognising which areas we're talking about in our formulae here, that's crucial. And here it's recognising both what albedo actually represents and then the ratio of the amount of the Earth that's hit by incoming solar radiation compared to the surface area of the overall Earth. Thirdly, estimate the average surface temperature of the Earth. That's much easier. You know that your intensity, power per unit area, is equal to E sigma T to the 4. Once again, we're going to estimate your emissivity at 1 because we have nothing else to contradict that. So we're modelling it as a black body, effectively. It is only an estimate, so that's fine. And so I have sigma 5.67 times 10 to the minus 8 times T to the 4 is equal to 245 watts per metre squared. That's what we've worked out. And I'm just going to do that all in one. So I'm going to take my value, divide it by Boltzmann's constant, 5.67 times 10 to the minus 8, and then take the fourth root of that value to get T is equal to 256 Kelvin to 3SF. And I just do a quick check in my head. Does that make sense? It seems a bit low, but it is of roughly the right order of magnitude. And when I read part D, it all may make a bit more sense. The average surface temperature of the Earth is actually 288 K, so it was a bit low. So just how the greenhouse effect helps explain the difference. Now, there are lots of things you could write about here. It's one of those real data dump questions. The greenhouse effect, in essence, is the idea that the Earth's atmosphere allows most incoming solar radiation to pass through it, but absorbs lots of infrared radiation. So the Earth itself, once it's absorbed this radiation that comes from the sun, gives off most of its radiation in the form of infrared, in other words, heat energy. And that is then absorbed by the atmosphere and re-emitted in both directions, therefore some of it goes back towards the Earth, heating it up. Now the actual marks here are a bit less detailed than that. There are 3 things you need to say, and you need to say 2 of them to get full marks. You need to say that the Earth predominantly emits radiation in the infrared spectrum. You need to say that greenhouse gases in the atmosphere absorb infrared radiation. Now, the reason they actually do that, and sometimes the IB does ask this, is that they resonate. So the resonant frequency of those greenhouse gases is approximately the same as the frequency of the infrared radiation. Therefore, they resonate, they're absorbed, whereas most other things are just transmitted through. And the final thing you should say is that then this IR is radiated in all directions, and so 50% of it, or at least some of it, heats Earth. It's not actually 50%, so I just put some of it heats Earth again. So it's effectively like having like a heated blanket around you, and it absorbs the radiation that's being given off by the Earth and then emits some of it back towards the Earth, compounding the effect. And that's why pumping more greenhouse gases into the atmosphere causes climate change, causes global warming. So I hope that's a bit clearer. As I say, it is the worst question that I've ever seen asked about this topic, and that's why it's so important we grapple with it now. And that's another, 8 marks? Sorted.